Hello and welcome to Mathenge Insight. I'm Zahra, and here I'll be sharing what I've been learning with you.
The most important transmission in the Ferrous Carbon diagram is the eutectoid transmission, where one solid phase turns into two solid phases. In this transmission, there are three essential lines: A1, ACM, and A3, and their location may be moved according to the condition. Microstructure is very important and determines mechanical properties. So, we must control microstructure after manufacturing to reach desirable mechanical properties. To observe microstructure, you just need to cut a small specimen from a part, utilize sandpaper for sanding, polish it, put it into the etchant solution, and then put it under the microscope. What does the etchant solution do? Etch solution is an acid. When we put the specimen in it, the part that have more energy burn and their color changes. So, this color difference allows us to see the microstructure under microscope. One of the most common compounds of etching solution is nitrile. During etching process, the color changes in area with high energies, such as grain boundaries. So it helps to distinct the grains, their boundaries, or their orientation. The microscope reveals some pictures. What are these pictures like, and what do they mean? When the specimen is placed at the austenitic temperature for a sufficient time, structure become completely austenite and with austenitic boundaries. Decreasing the temperature and solidification from this point with equilibrium condition bring about the eutectoid transmission. What does it mean? It means that from the bottom of the eutectoid line, austenite gradually turns into ferrite and cementite. Note that slowly. For example, it should be left in the furnace until it reaches room temperature or in the air. The way to cool it depends on the volume, size, and compounds of the specimen. During eutectoid transmission in equilibrium condition, what happened? First, a grain of cementite nucleate on the grain boundaries of primary austenite and extends into the grain, or it is created on impurity or secondary phases in the microstructure. It grows slowly in both length and weight, with approximately equal growth rate. Cementite needs more carbon percentage for growth, so the surrounding area have a lower percentage of carbon, and then the ferrite grains, which needs lower percentage of carbon, nucleate and grow. These layers of cementite and ferrite are called perlite. This process continues until this group of layers stopped by an obstacle, for example, an impurity, and the next group of layers will be created. Ferrite and cementite are both bright, and the dark lines indicating the interface. When you see this layered structure under the microscope, you will realize some important things like cooling rate. And this structure leads to low mechanical properties. Below 912, what is the effect of temperature on perlite? First, the formation of perlite occurs from below this temperature. In fact, the rate of nucleation and growth of perlite increases while the temperature decreases. The diffusion mechanism is dominant in the formation of perlite. The higher the temperature, the more diffusion occurs. On the other hand, the higher the temperature, the distance between the layers increases, so the diffusion of carbon becomes more difficult because carbon needs to take a longer path. In summary, between 600 and 700 more perlite grains will be nucleate and grow. If the solidification rate become out of equilibrium condition, different microstructure will be formed. For example, if the part stay long time in or above the eutectoid point, or the solidification rate in this range is very low, considering the percentage of carbon pre-eutectoid microstructure will form, and macrostructure will change and will not be full perlite. In this situation, if the percentage of carbon in the structure is low, ferrite grains are formed in austenite grain boundaries, and then perlite create. And if the percentage of carbon is more, cementite is formed at the grain boundary first, and then perlite will be formed. In this situation, perlite is dark, and also cementite is darker than ferrite, so it helps you to distinguish the pre-eutectoid structure. In a summary, an equilibrium condition brings about perlite microstructure, but if the solidification rate is a bit faster, a structure called Wittmann-Statten is created, and ferrite grains with needle shape are formed. The faster solidification, the more grain with needle shape will be formed. So the faster rate of solidification than Wittmann-Statten cause more needle-shaped grains and formed bainite microstructure, and much faster solidification rate like quench in water create martensite microstructure. In the next video, we will talk more about bainite and martensite.
Thank you so much for your attention. I hope you found this video useful. Comment your questions and subscribe for more tutorial videos. Bye.